This video is going to talk about the kinetic molecular theory, specifically how we apply this to gases. When we apply the kinetic molecular theory to gases, we have to make 5 assumptions. The first is that gases have large numbers of tiny particles spread very far apart. Basically, that they have almost no volume, which gives them a very low density. This is true of a gas if it's at a high temperature or a low pressure, but isn't always true. These 5 assumptions allow us to talk about the ideal or perfect gas. The second assumption is that there are no forces of attraction or repulsion between gas particles. There are actually some of these intermolecular forces, but they're so small that it's okay for us to ignore them. The third assumption is that particles are in constant, rapid, and random motion. If you remember the video of gas particles you watched 2 pages ago, those particles did move very fast and very chaotically. The fourth assumption is that particle collisions are elastic, which means they don't cause the particles to slow down because no energy is lost. This is true of the collisions between particles and between the particles and the container. The last assumption is that the average kinetic energy of the particles, which determines how fast they're moving, depends on the temperature of the gas. If we were to heat up a gas, the particles move faster. If we cool the gas down, the particles move more slowly. In fact, if we cool the gas enough, the particles move slowly enough to become attracted to each other again and become a liquid. When we're talking about the behavior of a gas, there are 4 factors we need to consider. First, we need to think about the pressure on the container. Second, we need to think about the volume of the container. Remember that gases expand limitlessly, so the size of the container they're expanding to fill makes a difference. The third factor is the amount of gas particles actually in the container. And the fourth is the temperature of the gas. When we're talking about temperature of a gas, we want to talk about it in Kelvin because there are no negative temperatures in Kelvin. We can talk about these factors using the kinetic molecular theory and gas laws. The first one is Boyles Law, and his law states that if the temperature does not change, pressure and volume are inversely proportional. That means as one goes up, the other one goes down. An example of this is a syringe. As you pull the syringe open, the volume increases, so the pressure decreases to the point where there's a vacuum, so it pulls in whatever liquid you're pulling up in the syringe in order to equalize the pressure. The second law we're going to talk about is Charles's law. This law says that when pressure is kept constant, temperature and volume are directly proportional. That means they both go up or they both go down. An example of that is when you crush a soda can using pressure. So you pour a little bit of water into a soda can, and then you put it onto a hot plate or stove to heat it up. Once you see a little bit of steam coming out, that means the water is turning into steam and filling up the can. So instead of there being just plain air, there's steam filling up that can a lot now. And then you turn it upside down in a glass of water, and you can see the can crushes. And this is because the temperature drops very, very rapidly, so the volume also has to drop very rapidly. The last gas law we're going to talk about is Gay-Lussac's law. This law states that when volume is constant, pressure and temperature are directly proportional. That means they both go up or they both go down. And some examples of this are with an aerosol can. The volume inside that can is constant. So when you spray, you're reducing the pressure, which also reduces the temperature of a gas. And if you've ever sprayed a lot of an aerosol can all at once, you might have felt the can get cold. Hopefully these real-life examples of these gas laws have helped you apply the kinetic molecular theory to your life.